Hi guys, so hopefully your mechanics revision is going well for your upcoming paper 3 exam tomorrow, or if you're watching this in years beyond 2023 when I'm recording this, hopefully your studies are all going fine. So I'm going to answer this question here, this mechanics question, and it's question 9 from the paper 3 Edexcel specimen paper. From the Edexcel syllabus. So this was a specimen paper, paper 3, and it's in the mechanics section of this paper. So even if you don't do Edexcel, it's still a question you could still watch this video, because mechanics is mechanics across every exam board. So it's a question about friction. So you got some friction involved in this question, and about ladders. So Edexcel especially, they do like these questions about ladders, leaning against walls, and moments and friction all involved in one. So this is a good question that we can work on. So let's have a go at working on this question here. So question number 9. So let's have a go at this. So we've got this uniform ladder, AB with a length of 2A and a weight of W. Okay, so what we know, I mean, if we just zoom in a little bit, let's just zoom in and try and get some forces on this diagram. So you've got a weight of W, length of 2A. So what we assume with these questions, especially when you see this word uniform means that the mass is distributed equally amongst, throughout the ladder. So it means your center of mass, so we're going to take the center of mass to be in the middle. So A, so like a length of A from this capital A along. So you've got your weight of W there. Watch out as well. This is a weight. This is W, an actual weight. So this is not a mass, not a mass in kilograms. This is W newtons of weight. Okay, so we got this. We got a coefficient of friction on the ground of 1/4. So you got this coefficient of friction on the ground. So you could have, let's just say you got friction going in this direction here. I mean, in theory, it could be going in the other direction, friction. I mean, remember, friction goes in the direction that opposes your motion. So, I mean, let's just say, for argument's sake, the friction's going in this direction. And we've got a coefficient of friction, a mu value of 1/4. Okay. The end of B is of the ladder. So at the end B, we're resting on a smooth wall. So there's no friction here. Let's just make a note here that there's no friction. So there's no friction on our wall. So we don't need to worry about friction on this wall. So if there's no friction on a surface, remember that your reaction force is perpendicular. So we've got a perpendicular reaction force. I mean, your normal, so remember, I made a video about this, 7 huge mistakes that mechanics students make. So remember, we've got our normal reaction force there. So I'll call this N, but the magnitude of your reaction force isn't always perpendicular. So it's always perpendicular if there's no friction. So the reaction force at B here, I mean, it will be perpendicular, but if you were to have friction, let's just pretend. So let's just pretend that there's some friction. So I'll call this pretend friction. So pretend friction. Then the magnitude of your reaction force, if we just I'm going to copy this arrow, the same length, and I'm going to move it up there. So I'm copying the arrow, same length there. So the magnitude of your reaction force would be going in this direction, but there's no friction here, so we don't need to worry about it because there's no friction. So your reaction force is exactly the same as your normal reaction force, this N then. We're going to call that force there M. Okay, so we got that. So then the next part, so we've got a builder of weight 7W stands at the top of the ladder. So you've got this builder going to stand on the top of the ladder up here. So I'll do it in blue again. It's got this ladder, top of the ladder up there, and he's got a weight of 7W. He's got 7W newtons. Sorry, 7W going down here. So 7W. Okay, great. So we got that, and what else we got? So to stop the ladder from slipping, the builder's assistant applies a horizontal force of magnitude P to the ladder at A towards the wall. Okay, right. So we got this force P, which is going towards the wall. So we're acting. So imagine this force P is acting at A, and it's going towards the wall, and that's the force we're adding. And yeah, the force is in a direction which is perpendicular to the wall. So yeah, it's going horizontal. Obviously, the wall's vertical. The P force is perpendicular. Okay, so the ladder rests in equilibrium. Okay, so it's in equilibrium, so it's not moving. So basically what that means, remember what that means, equilibrium, is that upwards forces equals downwards forces, and forces going to the right equals forces going to the left. So when we resolve our forces, that's what we got. And it's in a vertical plane perpendicular to the wall. So it just means, we're dealing with 2D motion. That's all it means. And makes an angle of alpha to horizontal, where tan alpha is 5/2. So we got this angle of alpha there. and the question tells us that tan alpha is 5/2. So let's just kind of let's kind of make sense of what that means. So we know that tan alpha equals 5/2. So if we draw like a triangle like this, so we've got our alpha there. Now remember, tan is opposite over adjacent. So we can just call this opposite side of this. We're going to construct like a right angle triangle. We'll call the opposite side 5, and this adjacent 2, opposite over adjacent 5/2. So what's our hypotenuse going to be? Well, using some Pythagoras, it's going to be the square root of 5 squared plus 2 squared. Sorry, just write that squared a little bit neater. So 2 squared. And this is going to be, so 5 squared, 25, 2 squared, 4. 25 plus 4 is 29. So we get the square root of 29. So we know that our sine alpha, so opposite over hypotenuse, is going to be 5/√29. And we know that our cos alpha is going to be adjacent to over hypotenuse √29. So I'm just going to, put a box around those two facts there, because especially in these, moments and rods and friction questions and components of forces, these sine and cos values always come up. So, that's going to be really helpful. Okay, so we got that information there. So then the builder's model is a particle. Okay, we know that. And the ladder's model is a uniform rod. Okay, yeah. So we want to show that the reaction force of the wall on the ladder at B has a magnitude of 3W. So remember, as we were saying a few minutes ago, the reaction force of the wall onto the ladder at B is this force here. So this force here. So again, if there were friction, we would actually have to do Pythagoras. You'd have to do like the friction squared plus the normal reaction force squared, square root that. But there's no friction on the wall. So the reaction force is literally N. So the question just wants us to find M. So again, if you're a bit unsure about what I'm talking about, please do watch my video on 7 huge mistakes mechanics students make, where I go through the distance. I go through the difference between a normal reaction force and the magnitude of a reaction force. So this part A of the question wants us to find N. So you've got to find this N force here. So a couple of other things I'm going to just add in as well. One more thing that I need to add in is the reaction force A. So remember, we've also got a perpendicular normal reaction force A as well. So just remember that there too. So we've got all our forces acting on this ladder drawn in on our diagram. So, I mean, we know that the ladder's in equilibrium. So I guess let's just see if we can, resolve some forces and see what equations we get with this question here. So let's see if that gets us anywhere close to the answer. So again, we want to find this normal reaction force, this N force going to the left, acting at B. Okay, so let's do some resolving forces. So it's in equilibrium. So ladder is in equilibrium. So therefore, we know that forces, so horizontal forces, forces going to the right are equal to horizontal forces going to the left. So what are our horizontal forces going to the right? So we've got P. So P is going to the right, isn't it? So this P force there, that's going to the right. And so is the friction as well. The friction is also going to the well. I say friction is going to the right, but we actually don't know. I mean, it could be going to the right or it could be going to the left. It depends how big this P is. So what I'm actually just going to say here is I'm going to say that the P force plus or minus the friction is equal to the horizontal force going to the left, which is this N force here. So this N going to the left, which we want to calculate in the first place. So that's our N force. So why have I put a plus or minus friction there? So again, let's just go through this. So friction could be going to the right, or it could be going to the left. So friction could be going right, or the friction could be going left. I mean, we don't, to be honest with you, at this moment in time, we don't know. I mean, if there was no P force there, so forget this P force there, there's no P force there, then the friction has to go to the right, because this normal force, this normal reaction force is going left. So you have to have friction going to the right to balance that, so that the ladder remains in equilibrium. But we've got this P force here, and this P force is going to the right, but we don't know if that, so if we've got a massive P force, then the friction is going to go to the left to counteract that. But if you've got a tiny P force, then the friction is going to go to the right because this normal reaction force is going to exceed P plus friction. Do you get what I mean? So we don't actually know the direction of friction. So we don't actually, yeah, we don't know yet. We just don't know. We don't have the information. I mean, we know the coefficient of friction is mu, and we can try and work out the maximum friction, so we can do that, but we don't know where the friction is going, whether it's going right or left. So that's why I'm putting the plus or minus sign there. But we can work out maximum friction. So remember our formula for friction. So remember that friction is less than or equal to mu times r. So again, we've got to be, really careful about this. Friction is less than or equal to mu times r. So it could be, so maximum friction is equal to mu times r, but friction in general is less than or equal to mu times r. So again, if you're unsure about this, please do watch my video, 7 huge mistakes that mechanics students make, where I go through why you've got the inequality sign there. But we know that maximum friction, so when the system is in limiting equilibrium, we know that maximum friction is equal to mu times r. Now, the question, if we read through the question, I mean, it says that what does it say? I mean, it says that, yeah, the ladder's in equilibrium. It doesn't say limiting equilibrium. So remember this term, limiting equilibrium. So if the system is in limiting equilibrium, then it means friction is at its maximum. So this would be limiting equilibrium. So if you see in your exam, so if you're watching this like the day before your paper 3 exam in 2023, limiting equilibrium just means that friction equals maximum friction. But we don't have that in this question. We just told equilibrium. So the friction could actually be less than mu r. We don't know. But I mean, let's just work out our maximum friction, because I'm pretty sure that's going to be helpful. If it's not helpful with part A of the question, it's going to be helpful in part B and C. So, let's just work that out and see what we get. So we know that maximum friction is equal to mu times r. Now, what is our mu? So the question told us what mu was. So 1/4. So just put this here. So mu is 1/4. And then times by our reaction force at A. So the reaction force, where the normal reaction force, where where the ladder rests on the ground. So this R there. Now, how could we calculate this R? So again, remember, the rod is in equilibrium, the ladder is in equilibrium. So forces going to the right equal forces going to the left, but also forces going upwards equals forces going downwards. So again, we know that because the ladder is in equilibrium. Also, forces going upwards, so forces upwards, so vertically upwards, equals forces vertically downwards. Really, I mean, if I was doing this in the exam, I'd include the word vertically, but just to be very clear to the examiner what I mean by quote upwards and quote downwards. But forces vertically upwards equals forces vertically downwards. So let's go back to our diagram, our force diagram. So we got this R, which is pushing the ladder upwards, and that's it. I mean, that's the only force going upwards. And then we got this W going downwards, and then this 7W also going downwards. So, okay, so we know that the force going upwards, which is just the R, is equal to the W going downwards, the weight of the ladder, plus the builder and his weight, 7W. So we know that the R is going to be 8W. So our reaction force, our normal reaction force acting at A is 8W. Okay, so then what does that all mean then? So it means our maximum friction is going to be 1/4 times R. So our maximum friction, so max friction is equal to 1/4 times by 8W, which equals 2W. So we know that piece of information as well. Now, again, what's the question asking us? The question's asking us to find the N, this N force. So the magnitude, so the force of the wall on the ladder B has a magnitude of 3W. We want to show that that force N is 3W. Now, okay, we've calculated the maximum friction, and we know we've got this formula here that P plus or minus friction, depending on the direction of friction, is equal to this N. But I mean, we don't know P. I mean, we know maximum friction, but we don't know P. So how are we going to calculate the N? Well, we're kind of at a dead end now. So the point of what I was trying to show you here is that with these mechanics questions, especially these ladder ones and these rod ones and these, ones where you've got distances on rods and that kind of thing, resolving forces is very helpful. And trust me, this resolving forces that we did here is going to be helpful for part B and part C, but it doesn't help us answer part A. I mean, we kind of got an idea of what's going on. It's good to do these resolving forces. So, but with this specific, question, we're kind of at a dead end. But that's fine. That's fine, because it's going to help us out later on. but we haven't really made much progress in finding m. So we tried to resolve forces, that's not worked. What other technique could we do to get this n force? We have to use moments. Okay, so we've got to use moments. We've got to try and use moments to get the n force, because that's the only technique we've got left. So what we're going to do is we're going to realize that, okay, we don't know this force P acting at A. We don't know the friction. We know the maximum friction, but we don't know the friction. We know the reaction force 8W, but we don't know the P. We don't know the friction. So let's eliminate those two unknown forces, the P and the friction. Let's take moments at A. So the whole point of this question is that we need to take moments A so that we can kind of forget about those two unknown forces. So what we're going to do is we're going to take moments about A. And again, what that does is, because if we look at our diagram, we don't know P, we don't know the actual really specific friction, but if we take moments about A, we don't need to worry about these two forces, because remember that the moment of a force, remember our formula, moment equals perpendicular, so equals distance, from the from A. So if we take moments about A, that's going to be distance from A. So distance from A times by the perpendicular force. So the force which is perpendicular to the distance from A. So the distance from, obviously this P force is acting at A, so the distance the force P is away from A is 0. So we can disregard that force, we can forget about that force, and also the friction as well. So that's why taking moments at A is a really useful trick with this question here. So that's what we're going to do. Let's take moments at A. So again, the rod is in equilibrium, the ladder is in equilibrium. So that means that our anti-clockwise moments, clockwise moments are going to be equal to our anti-clockwise moments. So the forces, so the moments of the forces that are trying to pull this. So imagine you've got your like a pin, like some kind of like pin, or your finger. You're going to put your finger down at A there. You're going to fix the ladder. You're going to forget about this wall. You just got a ladder like hanging up. You've got, obviously you've got forces which are going to want to push you, which are going to want to rotate you around clockwise. So you've got some forces that want to rotate you around clockwise if you've got this pin fixed at A, and you've also got, you've got one force, this N, which is trying to push you around anti-clockwise. So it's trying to spin you around anti-clockwise. So let's look at our clockwise moments first. Let's look at what forces are trying to pull us around clockwise. So it's this W here, this weight of the ladder, this W, and it's also this 7W as well. These two forces are trying to pull us anti-clockwise. Sorry, they're trying to rotate us around clockwise. So the key thing to notice now is that obviously we've got this W force there. Let's just focus on the W force. So if we want to take the moment of this if we want to find the moment of this W force, remember the formula, moment is equal to distance from A times by perpendicular. Sorry, I forgot the word perpendicular force. Let me just write that word, perpendicular force. So it's perpendicular force. So that's our formula. Now, remember that this W acting downwards in the middle, so like this W acting vertically downwards, is not perpendicular to the ladder, is it? It's not perpendicular. So we've got to take a component of this force. So we've got to do this kind of thing where we take components, and we want this component here. So let's put like a tick by there. So we want this component of the W perpendicular to the wall, perpendicular to this distance of A. So remember, the center of mass is halfway along the rod. The rod is 2A long, so A is halfway between that. So we want this perpendicular component, and the same as well with this 7W. Again, we want this perpendicular component. So this 7W is not perpendicular to the wall, so we want to take a perpendicular component. So this component, and again similar with this one there, a perpendicular component which is now perpendicular to the ladder. So that's what we want to do. So let's try and draw like another force diagram so we can be really clear about what's going on here. So you got your ladder, you got your 7W going down there, you got your angle of alpha. So that's our angle of alpha. You got your W there, you got your 7W going down there. Okay, so we're going to take, again, this is a distance of A, so that distance there is A. This is a distance up there of 2A. Okay, so we're going to take our perpendicular component of this W force. And remember, using your facts about angles, that must be alpha there. So hopefully that makes sense. Hopefully you're comfortable with why that's alpha. And then, okay, so we want to get this you've got a right angle triangle. This is supposed to be a right angle triangle with W as your hypotenuse. So you've got hypotenuse. You want the adjacent hypotenuse. That's cos. So this adjacent side is going to be W cos alpha. And again, similar with this 7W component here. So the component of this weight perpendicular, so perpendicular to the ladder, is going to be, again, that angle there, same angle of alpha. So it's going to be 7W times by cos alpha. So hypotenuse times by cos alpha equals your adjacent. Okay, so I mean we know what cos alpha is because we actually did this calculation up here, didn't we? So we know that cos alpha is 2/29. So let's just write this down here. So so we know that this component there is 7W times by 2/√29, and that's going to be equal to 14/√29 W. And then this component over here, so that's just going to be W times by cos alpha, and cos alpha again is 2/√29. So we got W times by 2. Sorry, this should be a number 2 there. So 2/√29, which is just going to be 2W/√29. So our clockwise moments, so we just focus on our clockwise moments. So these, remember, we're fixing at A there. That's A, capital A. We're fixing the ladder at A. We've got these perpendicular components which are trying to rotate us around clockwise. So our clockwise moments, so that's going to be this one plus this one. So our 14, sorry, my bad. Remember, moments is force times distance. So it's going to be this force. So this first force is 14/√29. So √29 W times by the distance from A. We're taking moments, remember, taking moments about A. So the distance, this force is, this perpendicular forces from A is 2A, this length there of 2A, so 2A. So times that by 2A. So that's our first moment. And then we're going to add our second moment. So again, distance. So the distance from A to the center of mass is just A. So it's going to be A, and then times by this force, this perpendicular force of 2W/√29. Okay, brilliant. So now we can just add those together. So 2 times 14, that's going to give us 28. So we get 28 AW/√29, and then plus 2AW, so 2AW/√29. We've got a common denominator, √29. 28AW plus 2AW, that's going to be 30AW. So that's the sum of our our clockwise moments. So that's the clockwise moments there. So clockwise moments. So the sum of the clockwise moments, really, I should say. So sum of clockwise moments. Now let's look at our anti-clockwise moments. So again, let's think about our anti-clockwise moments before we draw like another diagram for this. So again, same ladder, angle there, alpha. You weight, this weight there, trying to pull you around clockwise, and then this way again, trying to pull you around clockwise. But remember, we got this ladder, this wall here. This is our wall. And then you've got this reaction force, this normal reaction force, which is what we're trying to calculate in the first place in this question. And this normal reaction force is trying to push us around anti-clockwise. But again, the key thing to remember is that this normal reaction force, which we want to calculate, is not perpendicular. So this angle, there's not a right angle, is it? No. So what we've got to do again is take components of this normal reaction force. So again, if I just draw the diagram like this, so that's your wall. Imagine that's your wall again. This is your normal reaction force. So what do you have? So perpendicular. So again, you've got your ladder like that. So what you want to do is you want to take components. So that's your N force there. And then you're going to make, so this is going to be the hypotenuse of a right angle triangle. And then you're going to construct a right angle triangle like this, where that's your right angle. And the perpendicular component is going to be this component, isn't it? Because that is perpendicular to the ladder. That makes a right angle. So you want this component here. So we've got this right angle triangle like this with N there. And we want to try and find this component. Now, remember, so look at this diagram here. So what we've got here is you've got two parallel lines. That means we've got a parallel line there, parallel line there. You've got an angle of alpha there. So that's going to be an angle of alpha there as well, isn't it? Because alternate angles. Remember your Z angles from GCSE? So that's alternate angles. So you've got this N there, this N force there. and that angle there is alpha. So we want the opposite. We've got the hypotenuse. Sine is opposite over hypotenuse. So your opposite is your hypotenuse times sine. So this question mark here is going to be n times sine alpha. And remember that sine alpha from the question, if we just scroll up again, so we calculated that sine alpha is 5 over root 29. So just going to plug that in. So 5 over root 29. So this is going to be n times by 5 over root 29. So our anti-clockwise moment, we've only got one of them. So we've got no other forces trying to pull the ladder around anti-clockwise. So our anti-clockwise moments, well, the sum of them, because you've only got one, so sum of anti-clockwise moments is just the anti-clockwise moment we got there. So sorry, the force, that perpendicular force, times by the distance. So what's the distance from A, this fixed point A, to this normal reaction force? Is 2A, because the ladder's 2A long, isn't it? So it's the length of, as we can see up there, length of 2A. Okay, so it's going to be 2A times by our perpendicular force, which was this n times 2, sorry, 5, sorry, it was 5, wasn't it? So 5 over root 29. So we can just, again, simplify this. So 2 times 5 is 10, so you get 10 an over root 29. That's our anti-clockwise moment. Okay, so anti-clockwise moment equals clockwise moments because it's in equilibrium. So that means that therefore what we can say is that this here, so I'll just put like a black box around this. So this is our our sum of our clockwise moments. Let's just box this off. So this is the sum of our clockwise moments there that we calculated is going to be equal to our anti-clockwise moment. So this one there. So therefore we can say that 10 an divided by root 29 is equal to the result we got back here, this 30 AW over root 29. Okay, so 30 AW over root 29. Now, remember, what does the question want us to do? The question wants us to find n. So we're nearly there. So find the reaction force on the wall at B. So we're nearly there. So how are we going to do this? We've got to make n the subject to the formula. Well, first and foremost, notice that we've got A on the left-hand side. So we've got a multiple of A on the left-hand side, and we've got a multiple of A on the right-hand side. Divide both sides by A. The A just cancels out there and there. Also, if we times both sides by root 29, the root 29s just cancel out. So therefore, we're going to be left with 10n. So this is, sorry, just be really clear. This is not 10 newtons. This is 10n. N, the force, n, the normal reaction force, is equal to 30 times W. So therefore, your n force is going to be 30 W over 10, which is 3W. And that is exactly what we had to find. So if we go back to the question, show that the reaction of the wall on the ladder has a magnitude of 3W, and that's our question done. So this n force is 3W. So when you label your force diagram, if you're going to call this reaction force 3W, sorry, if you're going to call that reaction force n, just make sure obviously you label in your force diagram n, and then when you write your final answer, n equals 3W, the examiner knows what you mean. Okay, so that's the first part of the question done. So let's go on to the, sorry, my pen tool's not working. Let's try this. Okay, let's go on to part B. So part B of the question says, find in terms of W the range of possible values of P for which the ladder remains in equilibrium. Right, so we want to find the range of possible values of P. Now, this kind of links into what we did when we resolved our forces. So actually this equation here is going to be very, very helpful. So remember, obviously in part A, we tried to do this resolving forces method. We came at a dead end, didn't really get us anywhere, but this is going to be really helpful. We want to get a range of values such that a range of values for this P force such that the ladder is still in equilibrium. Now we know, because we've already done the hard work really, the ladder is in equilibrium if P plus or minus friction equals N. Again, we don't know the direction of friction. The question doesn't tell us, right? Could be going left, could be going right, okay? And again, just to re-emphasize, if there was no P force there, so if there was no P force, the friction would have to go to the right. So it'd have to go to the right because there's no other horizontal forces. But we don't know this P force. So this P force going to the right could be really massive. It could be so big that actually the ladder is going to the right. So your friction is going to counteract that. We don't know. So basically, what I'm trying to say is we don't know yet the direction of friction, but we do know that friction plus or minus, sorry, P plus or minus friction is equal to your force going to your normal reaction force that we just calculated. So let's copy out this equation that we got again, because it's going to be really helpful. So this P force plus or minus this friction force that we don't know is going to be equal to our N. And remember, we just calculated them. N is 3W. So P plus or minus friction is equal to this 3W that we just calculated. Now, let's think about this. So remember that our maximum friction, and we actually did this calculation already. So again, it's a good idea that we did the calculation we did at the start in blue here in part A, because actually this really helps us out in part B. So we can see from part A of the question that the maximum friction we calculated was 2W. Okay, so let's write this down. So from part A calculation, we see that maximum friction, so max friction, is equal to 2W. So therefore, if the ladder is in equilibrium, then therefore P plus or minus 2W is equal to sorry. No, let's forget that. Sorry, let's forget that. Right. So what I'm going to say now is that, okay, so if the ladder is in equilibrium, right, we know that the friction must be between well, obviously the maximum friction is 2W. So let me go back to the diagram. Let's forget what I was going to say there, because that wasn't quite right. Let's go back to the diagram. So again, the friction could be going to the right, as we can see here. So it could be going to the right there, or it could be going to the left, this friction. Okay, it could be going right, could be going left. Now, we know the maximum friction. Let me actually just draw another diagram here so we can see. Not like this, I'll do it like this. So we know that the maximum friction going this direction could be 2W, or in this direction, it could be 2W in that direction as well. Because again, this friction is just a magnitude. So the magnitude of this force could be 2W to the left, or it could be 2W to the right. So we don't know the direction, but we do know that basically it's either going to be between two. Yeah, the force going to the right could be up to 2W, so between 0 and 2W, and the force going to the left could be between 0 and the friction going to the left could be between 0 and 2W. So basically the friction, so the magnitude, so like the modulus of this friction force, actually let me be very clear. So the modulus, no, actually, let me just use the modulus signs rather than using words. So the modulus of this friction has got to be less than or equal to 2W, okay? Because that's how big the friction must be. So basically what that means is that if the system, so if the ladder is in limiting equilibrium, let's write this here. So if the ladder is in limiting equilibrium, so remember, limiting equilibrium means friction is at its maximum possible value. So if the ladder is in limiting equilibrium, so in limiting equilibrium, therefore that means, so this means that P, so P plus or minus your maximum friction force, so plus or minus 2W, is equal to your normal reaction force of 3W. So therefore P is going to be equal to 3W, and then take away your plus. So if you've got a plus or minus 2W there, if we do minus or plus 2W on both sides, we get again another plus or minus 2W. So either when friction is maximum, so at maximum friction, so either at max friction, P is equal to 3W take away W, sorry, 3W take away 2W, which is W, or the P is 3W plus 2W, 5W. So that means that the P must be trapped between those two values. So this force, P, is between W and 5W. So the magnitude of the force, this horizontal force that we're going to push the ladder with, is between W and 5, sorry, not 3, did I say 3W? Sorry, 5W, right? So it's between W and 5W. Again, because the friction could be going to the right, and that's anywhere between 0 newtons and 2W newtons, or the friction could be going to the left. Again, we don't know the direction, and that's anywhere between 0 newtons and 2W newtons. So altogether, the P value must be between W and 5W. So that's your final P there. So hopefully that made sense, but any questions, do let me know in the comments. And then the final part to this question. So often in practice, the builder's assistant will simply stand on the bottom of the ladder. So, okay, we've got to be careful with this question. I remember doing this question with a student before, and I made this mistake as well. If we go back to this paragraph here, to stop the ladder from slipping, the builder's assistant applies this P force. So this P force before was coming from the builder's assistant. So this is from the builder's assistant. So I call this BA for builder's assistant. So now we're going to get rid of this P force. So let's just make a note of this here. So with part C, we get rid of this P force, and the builder's going to stand on the bottom of the ladder instead of a P force. So let's just make a note of this here for part C. So in part C, so now P disappears, this P force disappears, builder's assistant, so builder's assistant now stands on ladder at A. So let's draw like a diagram of what's going on here. So you've got your ladder again like that. You've got no more P force, but you've got this builder here who's going to stand at A, and he's got some weight. I'm going to call the builder's weight B. So this is equal to the builder's assistant's weight. So builder's assistant's weight. Now you've got the same things, so like you've got the same center of mass there, so you've got the same weight there. You've got the same 7W going down there. You've got your reaction force here, so you've got this reaction force, and then you've got your normal reaction force there, so the same as before. So what we've got to be aware of is that if we take, so I mean, we've got obviously, you know, the rod must be in equilibrium, the ladder must be in equilibrium, and we've got to explain how this helps out. So how does this help the ladder from slipping? So in other words, you know, how does this basically increase the friction? It's basically what the question is saying. So to stop something from slipping, you have to have more friction. That's what the question is trying to get you to think about. So if you want to stop something from slipping, you need to increase friction, right? So that's the question wants you to explain, how does this now increase friction? So let's think about it. So we go to the diagram. So remember, to keep the ladder in equilibrium, to keep in equilibrium, we need to resolve forces, okay? So we need our upwards forces, so upwards forces to be equal to downwards forces. Now, if we've got this builder, well, builder's assistant standing at B, it means we've got more downwards forces. So that now, in this diagram, so now our downwards forces are forces are bigger, right? So our downwards forces are bigger due to builder's weight, due to builder's assistant's weight. So I'm just going to say BA as builder's assistant's weight. Okay, so the downwards force. So all of these. So if you add up the B there, the W there, the 7W there, you've got more weight going down. So that means your R has to increase. So your reaction force is now increasing, right? So therefore, R is now bigger than before. So R is now bigger than before. Okay, so we've got a bigger reaction force than before. Also, and this is really key as well to mention, is that the normal reaction force here is not changing. So I mean, if the normal reaction force here were to increase, or if it were to decrease, it would change the friction going to the right here, wouldn't it? So, you know, the normal reaction force would have to be equal to, you know, in order for this, you know, for the system to remain in equilibrium, again, your forces going to the right equals your forces going to the left, right? So now, again, you know, by someone standing here, your friction there, again, as I was just trying to say, your force going to the right equals your force going to the left. So the normal reaction force is not going to change. So why is your normal reaction force not going to change at N, this N here, this N acting at B? Well, that's because if you take moments at A, it's the same calculation as before. So, so we know that the reaction force on the ground is bigger than before. And also this N force, so the N force doesn't change. So why doesn't the N force change? So again, because if we take moments, so if we take moments, about A, then basically it's the same calculation we had before, isn't it? So we take moments about A, then we forget about this R force, we forget about this friction force. There could also be like another force as well. Maybe there's like another assistant pushing a force Q there, but we forget about all these forces and we just focus on this force, and this force. So that's exactly the same calculation as we did in part A, isn't it? Exactly the same calculation, right? Regardless of what new forces are happening at A, if we take moments about A, nothing's changed up here on the diagram. So the end doesn't change. So if we take moments about A, it's the same calculation as before. So it's same calculation, as before. So the calculation is now not changed as compared with before. Okay, so the end's not changed. So the end remains the same. So therefore, n remains same. The R at the bottom, so this reaction force is now bigger. Reaction force is bigger. R is bigger. So therefore, the maximum friction increases. So maximum friction is equal to mu times by a bigger reaction force. So bigger, sorry, let me rub that out, bigger R, right? So therefore, the maximum friction available is bigger. So therefore, more maximum friction available. So therefore, this helps to stop ladder slipping. Brilliant. So that's how we would answer that one. And again, the reason why we need to mention about this N force, this normal reaction force, but so we've got to include that to get one of the marks, is because if this normal reaction force were to change, if that were to be different, then that would impact the amount of friction available, right? So that's going to have an impact of friction. But because it doesn't change, right, then that doesn't have any, impact compared with before. So we just got to mention that the normal reaction force is the same as before due to moments. But because your reaction at A, this normal reaction at A, is bigger because we've got this extra downwards force due to the builder's assistant, that means that the maximum friction available is bigger. So there's more friction available. So it helps to stop the ladder from slipping because there's more friction able to stop that ladder from slipping. So hopefully that makes sense, but please do drop a comment in the comment section below if that doesn't make sense. So any questions, do let me know, but hopefully that helps you prepare for your upcoming mechanics exam.